In which format do you want to get the Excel file? Because I have Office 2010.
So no problem. So we already have the include the budget to file 2010.
Okay.
This is no problem.
So we start with the overall mass balance. So this is the Excel sheet you have got already for Mobile Arcade. And this is what we've got for Mobile Arcade. Yeah? This one. So you have one input, which is the target production, and then the scrap mix. That means in this case the DRI, you see, is calculated based on everything is calculated backward. Everything is calculated backward from this value. Okay.
The target
Target production.
target amount of the product is the first.
Yeah. Because we know the yield of the CCM, which is here, given by 100 minus these losses. These are the inputs, you see. And this is calculated value. So 97 is the result of these losses by, let's say, the strap, the skull, and the scales.
How to improve the scale amount? Is only for the experience?
Yeah, from experience. And in POSCO there is enough steel plants to calibrate these values. So then the CCM required steel is given by this calculation. And of course, between the CCM and the LF there is no loss. Yeah? So this is the same figure.
And in case of the, do you have some range from the CCM yield? Do you have some range data?
Yeah,
for
from
the CCM
97 to 98. There is no big variation. It just depends on the, let's say, the steel cleanliness requirements, how much steel you leave in the bottom of the ladle.
It is important to how much the slag amount inside of the ladle.
No. Because sometimes you don't need to, let's say, have the slag from the ladle in a turned shape. So you have to remake to keep certain amount of steel in the ladle. So it depends on the ladle capacity, etc. So then at ladle furnace you have losses. Due to the dust, due to the waste refractory and the slag, but this doesn't count for the yield. In fact, what is important is the alloys you put in there. To calculate this weight here. This weight, you see, is given by the amount of alloys, assuming a yield of 0.6. Of course, we could make a more precise calculation, but it is not the purpose at this stage of the project. So we have the total liquid steel from the EAF, and to calculate this value, you see, this is the this amount of steel, minus the carryover, of course, and assuming 20% of iron in the carryover,
You mean we carry over slab? Is it 20%
Yeah,
of the EAF? What
Yeah.
is it?
20% of the, in the EAF slag
In the EAF slab.
tacked into the ladle,
Uh-huh.
we assume 20% iron.
20% iron in the slab.
Yes. And minus the, plus this amount of scrap. This scrap is, let's say, the steel which is deslagged. Yeah, in the pit. So then you have the amount of liquid steel you have to produce in the furnace. Right? Then this is the total amount of raw material need, which is the steel divided by the yield. Yeah? And this yield is given by 6. The scrap, assuming a yield of 0.9, yeah? The purchase scrap, assuming a yield of 0.9, the home scrap having a yield of 85, and the DRI having a yield of 86.
0.9 and 0.85, 0.86 is a constant based on your experience
Yeah.
for the yield scrap and DRI.
This is for rough calculation, yeah? To give the customer an idea of the material balance he will have to handle.
이해 안 되면 즉각적으로 얘기를 하라고 좀 가만히 있지 말고.
So this gives you the amount of raw material. Yeah?
What if we don't use the DRI?
100% scrap.
100% scrap, of course. It will be better to present this data sheet a little bit different. We just cancelled the DRI and we put the purchase scrap here and we changed. It's easy. Yeah.
저 똑같잖아 지금.
Dr. DK, I'm sure you are able to handle this. Okay.
So I want I need some lime carbons, and
Okay.
other alloys.
This is here.
Yeah, this data is important. I think.
Yeah.
The data from we need more precise calculations, and then we can revise it. But I think it is based on your experience or your calculations.
No. These figures here are based on the material balance I've done for one heat. Yeah.
다른 시트에 지금
Okay, I could link this calculation sheet with the balance, the material balance of one heat. But in fact, I didn't do. I just took the results of the material balance and put it there.
Yeah, that's right. Okay.
You see, this is a constant figure. This is not the result of the calculation.
If we link that cell to the material balance, it is more easier. When we put in the material balance, and the sheet is also can change easily.
Yeah, but it's possible.
Okay.
That means it's possible to not to have this file as an independent file, but to have an extra, let's say, calculation sheet in the overall model, in the EAF model.
Okay.
Yeah, that's a good idea. That's a good idea.
I'm lazy, so I put it small.
So, this was the easiest part. So now let's go to the EF model. Well, it is organized in different sheets. You have the input data, the scrap analysis, the material balance, the thermal balance, the electrical power calculation, and the process diagram. So let's start from the beginning. Okay. So first of all, you have several buttons here to save the data or to let's say load from the memory. Yeah? So if I want to get back the yeah. So I guess we were using without MGO, yeah? I don't remember.
Finally, with the NGO.
With MGO, yeah? Okay. Ah, it's a different version because I still have the POSCO model here. Okay, never mind. The problem with this system is that you don't make the difference between just record information and the model itself. Check. Because these gentlemen from Microsoft, they have changed completely the programming of the solver in Excel. So between the 2007 and 2010, some macros are not no more available. Okay, but rejected.
엑셀 어디서 디벨로핑을 하는 게 나을 건지 소프트웨어 만드는 게 나을 건지 고민해야 되겠네요.
Okay, I can save, you see. And then you get a file with all the main informations. You see up, all is there. That means when in the future you don't need to save the complete file, which is anyway about 1 megabyte, yeah? And you can save room like that. You see, for example, it's just 105 kilo, and this one is 300. Okay, not so much difference. So it's up to you, yeah? Well, so in this sheet you put the main items from the project. So the furnace capacity, the furnace dimension, the shell diameter, water cool panel, the panel height. This determines the volume of the shell to calculate the basket number. Yeah? Yeah, the EF of the volume of the EF is given by this formula. Now very simple, yeah, we calculate the furnace vessel. And the basket number is given by the the tons of scrap. We will see where it's calculated, and divided by the density. AK3 is this one here, AK3. And divided by the volume, where we take only 95% of the volume for the safety, yeah? Because you have to give some freeboard, because the scrap density is changing between the basket and the furnace shell. Yeah? And there is one criteria which is important for the basket design, in order to avoid that the scrap density is too much reduced when you open the basket. Then there's liquid steel, the liquid air, the pitch circle diameter, electrode, bath depth, electrode diameter, and these are figures which are necessary to calculate the electrode consumption. Injection device. So you may,
all the technical data should be typed in.
yes, you see there is no formula.
And what about the pitch dial?
PCD,
Below.
PCD is also given. Yeah?
What's the elbow? Elbow dial and elbow height?
This is for further, let's say, extension of the model, but not yet developed. Yeah?
Extension of the model?
Because, in fact, you have different possibility to determine the thermal balance. You may take the off gas at the elbow, or you may take the off gas at the roof. For the time being, the thermal balance is defined at the roof.
Yes.
Yeah.
Is that for that reason? Using that one?
If you want to, because take as an example, like you install gas analysis to have, let's say, your own experience of what is a gas composition, gas temperature, and you install it at the elbow. So you have the features of the off gas at the elbow with some post combustion and heat losses in the elbow.
There is the elbow height, what is the elbow dial? Is that also same function? The elbow dial?
No. This is to calculate the surface of the elbow. For the time being, it's not used, yeah? So you may have conventional burners with only megawatts here in rating, or you may have something like cojet, yeah? So cojet, you know, with the flame rating, the oxygen efficiency, and the oxygen flow, the main oxygen flow, not the burner flow, yeah? Not the oxygen from the shrouding. This is the central oxygen. Yeah?
Center?
In the cojet, you have a central nozzle with supersonic, and this is this flow rate. Yeah.
For the coset, right?
We are not talking about the oxygen necessary to burn this 1.5 megawatt gas, natural gas. Alright? Then you have carbon lenses here, 2 or 3, and what we will need during melting and during refining. and you still have the possibility to have door lenses. Okay, this is inputs. All this is inputs. Then you have the still features with the tapping temperature and the tap cover, slag basicity, and the production hours.
So I have more questions. The main oxygen flow is for only the injection, injection, and when we calculate oxygen flow, total flow, we have to calculate from the 1.5 megawatt. 1.5 megawatt, it means the natural gas and oxygen combined make 1.5 megawatt.
It will be calculated.
Okay, I see.
It will be calculated, you will see. So you see here, you have the oxygen lens calculated here and the oxygen necessary for the burners. Right? And in the spec, you see, you have the oxygen, the total oxygen here, yeah? Because you have 5 cojets, 5 times 2,500 plus the oxygen necessary for this. And then you have the scrap mix here. Right? So you have here in these 2 cells, you see different charging procedure, not including in the bucket calculation. Here as well.
Same, yeah, of course.
But here you may put some HPI and DRI in the bucket.
Okay.
Huh? There is no...
HMS가 뭐야, 저기? 1m? Scrap? HMS means 1m scrap?
No, HMS is heavy melting scrap.
Melting scrap.
Yeah. This is, let's say, the American standard.
It's H1 and H2 class.
Eh?
H1 and H2 class, heavy melting scrap.
Whether you want to check if it makes 100%? Yeah, you see.
Why don't you mention the all percentage? Left side. HMS 32%, local 15%, auto bundle 10%, rebar 3% is total, makes 60% of scrap.
You forgot this.
That is 40%.
You see? This is 100 minus. Oops. You see, this is 100 minus all these values here.
Yes.
Okay? If I put here pig iron, if I put 10% pig iron, you see it gives 22%. Now I remove this. Okay?
Yes.
HMS 1, H1 그리고 HMS 2.
You see, we have 100%.
Okay, I see.
Happy?
Yeah, I'm happy.
25%. Here, 10%. Income 3. HMS 25. Alright.
How about if we used turnings? Yeah? Turning is 30%.
Yeah. So if you put 30%, you will see you get just 15% here.
Okay. What is changed? It's transformer data is the same.
The
Transformer data, the capacity is not changed. Yeah.
No,
No, not
For the
dependent.
time being, we have not yet calculated anything. We
Okay.
just put what the customer has told us for his intention to charge the furnace.
Okay.
Eh? You will see it's a little bit more complicated.
So I would like to put in the scrap mix. Yeah.
You see, this button is changing. Right?
In this age, in Japan, in Korea, the HMS 1, H1, we call H1, HMS 1, HMS 2 is not too much. It's normally the turnings and water bundles and bushes, shred is I think more than 50%, I think.
Oh yeah?
In these days, the scrap, low scrap. So how about putting the like this? It's HMS 1 and 2 is only 10%, under the 10%.
I mean, you can adapt, you can put whatever you want there. Yeah?
So I would like to know how to change the transformer data depending on the scrap mix. Is it?
No, because this depends on the target productivity you want.
Target productivity.
For let's say for this approach, then you need another model. Yeah. This is a simple model for the salespeople. It's not very precise, but at least. Shit. I have some problem with this screen. So. Oh, yeah. Okay. You put 1 million ton here. Okay. And you want to calculate the production time, then you have here to say I have 21 shutdown days, holidays, I don't know, 0. This is 3 weeks shutdown, annual shutdown. And I have 12 hours shutdown per week. Yeah, that makes, it's a lot, eh? 10 more days. So, now you know the production days. That makes you a productivity of 135 tons an hour. Yeah? And then you want to see, I have somewhere the scrap. Here I put the scrap mix. Yeah? So you say 50% shred, HMS2, how much?
10.
10. Local.
HMS 5. HMS 5.
Eh?
5.
No, HMS1 is the result of the calculation.
Yeah. HMS 2 5.
5.
Local is 30. 60.
60?
No.
Shredded.
Less than 40. That means, right?
No, but it's just a recommendation, that's it.
Shred 30. 30.
30.
20 or 30. Yeah, 30. And
Bushing,
turning.
turning. How much turning?
30.
So 5% HMS1. Right? Okay. So then you have to optimize the furnace size. Then you put DRI or hot metal here, you see. You want to know the furnace size. So for this target productivity of 135 tons an hour, in the furnace you can calculate, let's say, the power of time. For example, this is maybe optimistic. I put this in 5 minutes for the delay. 14 minutes power of time is more, let's say, safe, yeah? And so you see, if I have 120 ton, it needs 53 tons an hour. 53 minutes tap to tap. So, in fact, maybe I could, let's say, decrease the furnace capacity, yeah? So let's put 100 ton. So it calculates here from 100 to 140 and to see, okay, 44 minutes still to be okay. 103 MVA for 100 ton capacity is a good figure. Huh? So I get here 100 ton, power 144, power of 30 minutes, 118 MVA. Yeah? This is a disaster. So, and then it shows this is something you can print for the customer as well. So we didn't discuss about this model. It was designed for Fuchs, but it's not problem for you. So you see how you can get first a feeling about the transformer size you need to put. But this is a different philosophy here, where
저는 대략적으로 그냥
똑같은 게 들어가 있어.
in a previous version, of this software,
Do you develop the Hooks program and hand out to the Hooks? You changed your program, only the screens, only the. I mean, you developed your program and then you gave the software to Hooks technology, no? And then you only changed your figures, screen displays. What's different? It is the precise program, yeah. What is different? Whose technology software and your software?
Between these two, no, because I developed the previous one, yeah, for the salespeople. They want to have nice stuff with pictures and
I see.
fancy stuff. So
okay, it's the same function, but it
simplified.
Okay.
Yeah. Simplified.
Okay.
Because they wanted to have a tool to, let's say, get an interface between what the customer is requesting
Mhm.
I need to produce 1 million ton per year. And I guess, okay, I have, let's say, had a look around the world. I guess a 100-ton furnace would be convenient, which is important to design the structure of the melt shop, because a lot of money involved. And then, okay, what kind of transformer? So then the sales guy has immediately an idea of the transformer he has to implement. On this version, you see, I had this button to calculate directly the megawatts. I mean, I know that the furnace is going to use 380 kilowatt hours per ton. I want to produce 1 million tons, so I need average 64 megawatt. Average 64. So then you know that you will type here 70 and you will see what kind of productivity you get out of it. If you want, I can add this button here. It's not a big deal. Because now, by experience, I know more or less what is the power I need. So that's why I go directly and I put the megawatts here. All right.
저 아까 앞에 있는 것처럼 계산을 바로 선택할 수 있게 하는 걸로 낫겠네, 그지? Okay, keep going.
So we'll see this later. So this is the scrap analysis and let's say the fluxes analysis, where you can change according to the project. This analysis is the result of, let's say, my old experience in IRSID, where I made heat test with 100% of one kind of scrap.
Heat test?
Yeah. In the EAF, I put 100% of one kind of scrap.
One kind?
One kind of
All
scrap.
kind of scrap.
100% SMS1, 100% SMS2, etc., etc. And this is the result of about 120 heat tests.
120 heat. And you can get this data.
And I put this data. Of course, it's subject to variation. You know, scrap is never the same.
Yeah, that's right, that's right. But it's a similar, not big change.
So, in fact, this is what I'm using normally. But if I know that this steel plant, which has a project, is using very bad scrap, yeah, and their yield is approximately 88%. Of course, I will not use the standard analysis. I will, let's say, downgrade the analysis to reach the target. Yeah. But you have to have some feeling how much gain is in that scrap.
Yeah. It's briefly summarize your words. If the scrap yield is low, then your the recommended values, scrap yield, it's 88%. Euro is 97%, 98%.
Wait a minute. 86.
86%.
It's not balanced.
If the existing plant they have yield of scrap is 84%, we cannot use that table. We used some.
First, I put the scrap mix, what the customer is telling me. And then I come to the material balance, and I put the iron content according to, let's say, the practice he has. If he's doing a good forming slag or poor forming slag. If he over-oxidized the scrap with the cold jets, or if he's not over-oxidizing the scrap with the cojets.
Mhm.
And then if I don't get the yield, whatever he has, of course I have to adapt the scrap analysis. First, I try to use the standard scrap analysis.
Mhm.
Yeah.
Where do you test this? Where do you 120 times?
Oh, it's a long time ago.
But during the development time in hooks?
No.
Hooks? No.
Much earlier.
What was earlier?
It was in the 80s.
18th?
80s.
University or?
1980.
Yeah.
Between 83 and 90.
Mm.
7 years. Yeah.
7 years.
Yeah.
Okay. Good.
So it's a long time ago already, yeah. So
Mm.
maybe some refreshment would be necessary.
Mm.
Yeah. But I got also some, let's say, statistical data from the melt shop.
Mm.
So I mean, I made this analysis. Let's say I adapted this analysis.
Mm. Okay.
So here you have in this column. So you see, this is from everything is inside, yeah.
Mm.
So alloys here, carbon, silicon, mangan. The oxygen is very important.
Mhm.
This is the oxygen linked to the iron.
Mm.
It means this is the quantity of rust.
Rust?
Rust,
Rust.
iron oxide.
Uh-huh.
Yeah. And this is very, very, let's say, energy consuming. So of course there is no rust in the liquid iron and no GaN either. But in the DRI you have a lot of oxygen linked to the iron.
And so DRI needs more energy capacity, bigger energy capacity, 2.6 oxygen.
Due to the GaN
Mhm.
and due to the iron.
그건 다 이해했어요.
화학물을
산화 처리
VF5를 NLL 그러니까 더 많이 들어가는
열이 더 많이 들어간 거야.
이게 제일 중요하다는 거지, 체크할 때 우리가 산소량이. 오케이. Keep going.
So in this column you have the average of scrap, and in this column the average of scrap plus DRI or liquid iron and liquid iron. Yeah. This is to know that you will get in a basket, yeah? And this is after dilution with the DRI and the liquid iron.
So if the customers does not know their scrap density when we suggest average scrap, the right side columns, if the customer does not know or does not fix their scrap density, and we can suggest the right side.
Yeah, you can suggest, yeah, but the customer has to, let's say, provide a scrap density. This is his responsibility because we are not going, I mean, as furnace supplier, we are not going to buy scrap.
Yeah, that's right.
And the furnace will be designed for a certain scrap density.
But if at the beginning time, in the beginning or only the planning period of the project, the customers need our help, yeah, and they did not fix it. They did not decide.
Are you going to make the market analysis for the customer to know what is available?
Yeah, they know it, but in our case, before they analysis the market of the scrap, yeah, and they need what kind of scraps they purchase, yeah.
Look, if the customer has no idea about the scrap he is going to buy, he has better not to start in the business.
Yeah. But the
Because
first
look,
initial time.
The scrap, not initial time, the scrap represent 60 to 70% of the conversion cost in a melt shop. He has better to know what kind of scrap he will buy.
Obviously, before deciding to invest, they obviously check and investigate the scrap and scrap compositions. Yeah. But sometimes they ask us what is the best scrap mix, what is the composition of the scrap. It is, and they start to investigate the scrap market. And then we can use the average scrap compositions.
That can happen, but most of the time they prefer to do this job themselves.
Yeah, obviously.
Yeah, because I have a scrap evaluation model, but
Okay, fine.
What about the temperature, 400?
yeah,
The DRI current. Is that-
because sometimes you may have hot DRI.
Yes.
Yeah.
Does that also link to the functional calculation?
Yeah.
Okay. Would you please mention the right side of the average scrap after dilution? I don't know what to say. The right side, the average scrap.
Yeah.
What's that meaning?
Okay,
Of course, in this case, there is no DRI and no hot metal. Let's change a little bit. I remove the turnings and I put liquid iron. So now you see,
changed.
it's changed here.
Okay.
But this is just convenient for the next table. Here I have a scrap, then I specify liquid iron and DRI. So this is coming here from this column here. Otherwise I have to do the calculation twice. Okay. But of course you may have only one column for sure. I have initiated here a price in order to maybe in the future have the possibility to make the scrap mix optimization. But or to calculate the cost of the liquid steel.
지금 90달러나 원으로 쓰면 어떨까요?
유로 쓰면 바꿔도 기준을 바꿔놓고 그 비율을 곱해서
어차피
나중에
입력하면 되니까.
Okay, keep going.
So in the analysis as well, you have the water. You see that for turnings can be high. Then the GAN here. And most of the time the GAN is acid, that means there is more SiO2 than CaO. And the iron is the complement of this analysis. See 7% minus 7. Then down below you have the charged carbon and the injection carbon. And line and dollar line. Here is a small table to help you, because most of the time the DRI is specified not as like this, but you are given the metallization rate and the total iron. So you put these two figures and you have the amount of oxygen to report here. And if I put some DRI, you will see the calculation. you see that with this analysis, I have 120 kilograms of slag, and I need enthalpy of 542 kilowatt hours per ton.
Was that included all slag itself? The enthalpy?
Yeah. So this is the enthalpy of the liquid steel
Yes, yes.
plus the enthalpy of the slag,
Yes.
this one here, plus the amount of oxygen to be reduced. Yeah. You will see later within the material balance. It's to have a rough idea about what is going to be the power consumption. Eh?
Yes. Well, what's the meaning? DRI/HBI. Actually, what's the meaning?
What?
Exactly. DRI/HBI.
Yeah, because I mean it's named here DRI,
Yes.
but that could be as well HBI. Yeah?
Yes.
We can use the sometimes DI, sometimes the HBI.
I could add many other columns for other kind of raw material. Yeah. But once you have to stop, I mean.
Okay.
It's rather rare that a steel plant is using both
Yeah.
on a regular basis,
Yeah, it's a.
because he has either the DRI plant or the HBI plant just across, so they receive only one type.
The DRI plant make also HBI. They used some small powders, small granules. They make HBI.
Not all the time. In Hadid, they don't have this machine, for example.
I heard that they are feeding the DRI and they have screen for some sizes.
Yeah.
And the small granule or powders they
Yeah.
used to make HBI.
Or they are injecting.
No, I don't know. It's a small, what is it? Small sponges or injecting. No, they make a.
Because if you are doing pellets,
Yeah, pellets. Yeah.
the fine when you screen, the fines are
They make
recycled.
pellets. They make pellets.
Yeah, the fines are recycled in the pelletization plant, so they are circulating.
Yeah.
So it's rather rare that you are doing both, yeah? Because the HBI plant is rather expensive, yeah? Because you have to reheat. It's not done, let's say, in cold condition, yeah? It's done in hot condition. So you have to reheat only the fines to make the HBI. It doesn't pay off.
Okay.
So it may happen that they're producing both, but I've never seen.
Yeah, only I heard at Mubarak, they used some powder and some small granules to make the HBI. Only I heard. I cannot saw. I did not saw.
Or maybe they needed to buy something, I don't know. So this table is just to calculate the oxygen to put here. Huh?
Okay. And what about can? Can and basic means basicity?
This is the basicity of this gang.
Can is basicity, not the total basicity.
No. You see, it's this is this basicity
Scrap.
from scrap.
Okay.
Okay.
Yeah.
네, 메탈 밸런스.
So the material balance.
하나 10분 쉬고.
Okay. Let's take a break.
Let's take a break.
타이밍을 맞추고 있는데
아 그래요?
시작.
효율적인 학습을 위해 갖고 이제.
아니 내가 상무님 일사 시킬 때
아,
시간 맞추려고.
그럼 맞춰줘. 수고하시죠.
아예 꺼. 됐어.